referred to as something called the first messenger. Right? Because it's the first messenger. That makes this one the what? Second messenger. So how does my cell know that the first messenger is out there? Oh, because now we got something new inside the cell that's the second messenger. Okay with that? Then, once we have this second messenger, then that is going to alter something inside the cell, and then you're going to get the response. So this type of pathway here is called, often, we call this a signal transduction. If you know the vocabulary, it's easy. Signal transduction pathway. To transduce means to convert. So transduction just means conversion. So this outside signal was converted into an inside signal. That's the signal transduction pathway. Now, is it a single step? No, because then it wouldn't be a pathway, right? So A happens, B happens, C happens, D happens. Oh, finally, a response. This is a signal transduction pathway. It's a series of steps that occur. We often call it a cascade. You know, cascade refers to like water flowing over a waterfall or something, right? But it's literally A happens, which causes B to happen, which causes C to happen, which causes D to happen, which you get a response. Now, let's just stop for a minute and think about this. Cascades and transduction pathways in cell biology are ubiquitous, meaning that they're everywhere. Okay? It's not a little specific example where one happens. They're everywhere. So that must mean that there's something relevant or important or beneficial about a signal transduction pathway. Because otherwise, why don't you just have A cause B that gives you the response? Right? That's easier, right? That's probably energetically more efficient, right? But it must be at a trade-off with something. And what it's at a trade-off with is regulation. If you look at this, how much opportunity do I have to regulate this process compared to if I just had A, B, response? Which one has more opportunity to regulate and fine-tune? This one.
Cascade.
This is like I can regulate it right there and that's it, because as soon as I get B, I get a response. But on this one, I can regulate multiple pathways and multiple steps. Each step has an enzyme, right? So I can give different amounts of enzymes to build up this intermediate or something like that, right? So I have a lot greater chance to fine-tune the response if I have a multiple-step pathway. The trade-off is that there's more places for something to go wrong also, right? But it gives me that ability to regulate at a finer level. And so signal transduction pathways, and cascades in particular, are really ubiquitous in cell biology because they give us this ability to fine-tune the regulation at multiple steps. So you okay with that conceptually? So you're okay with differences between hydrophobic, hydrophilic. You understand that most signal molecules, just because I told you, are hydrophilic, so we've got a membrane surface receptor. That means that that must be linked to something inside to give us this intracellular response. And oftentimes that linkage involves the cascade of a pathway so that you get this transduction occurring over multiple steps. Is that okay? All right. This is the mechanism by which any hydrophilic signal molecule is going to have to operate. Any hydrophilic hormone, all the protein hormones, have to operate this way. Okay. And we'll see some specific examples of these cascades and these transduction pathways as we talk about specific hormone interactions. But there are a couple that are really common, and one in particular is very common. And so that's what I want to spend a little bit of time telling you about, is just kind of the general pathways that occur in signal transduction.